Hi, everyone. So first of all, thank you all for being here, and thanks to the organizers, and in particular to Yonuk, Professor Yonuk, for inviting me and inviting quantum machines to this conference. So indeed, today we will talk about aspects of designing control systems when you want to scale up from 1 to 100 qubits, and of course beyond, and also when you want to go from the typical quantum experiments like Rabi and Ramsey all the way to quantum error correction and other complex quantum sequences. So before we talk about all that, I want to start with two very important things. The first is that we're hiring in Korea, so we're also hiring outside of Korea, but in particular we're now seeking to have people, boots on the ground here in Korea. So if you feel you're relevant or know anyone, feel free to drop us a line. The second thing I'd like to do is introduce briefly quantum machines. So who are we at Quantum Machines? So at Quantum Machines, we're a team of quantum physicists and engineers on a mission to revolutionize quantum control and unlock a new era in quantum research. So this is what we're all about, and this is what we wake up in the morning for. At the core of the company, we have a very, very large team of quantum physicists that worked on pretty much all types of quantum platforms out there. Of course, superconducting qubits, trapped ions, neutral atoms, spin qubits, and so on and so forth. Worth noting is the team that you see on the left-hand side. This is the team from QDevil that we recently acquired, a company in Denmark. Another particular person that is worth noting is Nissim Ofek here at the top. So he's one of the co-founders of the company. Nissim was the first person in the world to ever demonstrate quantum error correction. He did that during his postdoc at Yale. And we're talking about error correction, not error detection. So this was one very big demonstration. So of course, we're a company and we have products, and in order to have products, physicists are not enough. So you also need engineers. By now, we're over 100 people in the company at Quantum Machines with over 200 customers, and we're spanning the entire globe. And this is all despite the fact that we started in 2018. And of course, you may ask the question, how come we managed to grow so fast, right? How come we managed to grow so fast, the company? And typically, if you see a company that is growing very fast, you know that they're probably solving a real problem, a real industry problem and unmet need. And let me explain a bit the problem that we're solving at Quantum Machines, and I think that many of you will relate to it. I'm going to explain it in the following way. So of course, we're all interested in quantum systems, right? Different quantum systems, this is what we're interested in. But in order to do anything with a quantum system, you always need to send pulses to it and get pulses from it, right? And since we are classical beings ourselves, it is a fundamental fact that we need other classical systems to mediate this process for us. And what the typical thing that you would do for many, many years is you would get a typical classical system like general purpose test equipment, right? AWGs, lock-ins, digitizers, and so on and so forth. These are amazing instruments. These are great instruments that I've also used them in the past myself. But they're amazing only until a certain point. And this point is when you want to run very complex quantum sequences. Okay, if you want to do something really groundbreaking, what you actually will find yourself doing with general purpose test equipment is work very, very hard. I'm sure that many of you have actually done that. Okay, months and years of FPGA programming, software programming, hardware development, synchronization of different modules, and so on and so forth. This is how we grew so fast. We actually solved a very particular industry problem. So now let me present to you the goal of this session. We're going to talk about what matters when scaling from 1 to 100 qubits, or alternatively, from running a Ramsey to running quantum error correction. What really matters when designing a control system. So we do it in 3 steps, okay, 3 different questions. The first thing is, how long will it take to implement a flagship experiment? Okay, if you now want to scale up to 50 or 100 qubits, you probably have some flagship experiment in mind. The question is how long it will take you to implement it, or any other algorithm or experiment that you will have along the way. This is the first question. The second question is, how fast do sequences and calibrations run? Okay, this is an extremely important question, because sometimes for calibrations, a factor of 25 may mean the difference between 2 weeks and a year, right? And the third question is, to what extent are the hardware and software scalable? Namely, how different is it to write a sequence and run a sequence for 1 and 100 qubits. So we're going to talk briefly about each and every one of these aspects, and I'm going to start with this first one. So excuse me for a moment. So how long will it take to implement a flagship experiment? So I'm going to tell you about that from our perspective at Quantum Machines. So the goal of a control system that you design should be the following. It should be allowing you as an experimentalist to run the most advanced quantum algorithms that you have in mind out of the box, namely without all that effort that I mentioned earlier, right? You want to imagine the new flagship experiment that you have in mind. You want to run it right out of the box without all that effort and from a super intuitive programming language. Okay, so how do we do that? Let me first describe it to you from an architecture perspective at the high level, and then I'll go deeper and deeper. So at the high level, the bottom line of the platform that you need, of the control platform that you need, should send pulses and get pulses, right? It goes without saying. This is the basic. The control system sends pulses and gets pulses. But the main new paradigm that we brought to quantum control is the existence of a processor, which we call the pulse processing unit, at the heart of the control hardware. And this pulse processing unit was designed from the ground up so that it can run even the most complex quantum sequences in real time. Okay? And real time is the emphasis. This is the most crucial aspect. Okay? And typically we decompose this real time into 4 elements. The first element is waveform generation, which we note here in a fully parametric way. So for example, you want to parameterize the amplitudes, on a nanosecond level. You want to parameterize things like the frequencies, the phases, global parameters of the sequence, and so on and so forth. In real time, not on your PC, in real time. The second is waveform acquisition. Clearly, you need to get pulses back from your qubits. This could be analog pulses. This could be digital pulses. This could be even images from atoms if you're working on ions or Rydbergs. The third is real-time processing. And real-time processing is very broad. We're talking about Turing-complete processing. So from the demodulations and integrations that you apply to typical pulses through thresholding in the IQ plane for state estimations, error estimations for error correction, Bayesian estimations for adaptive sensing, and so on and so forth. The fourth element that should and must happen in real time is control flow. Control flow is just the good old if-else statements, for loops, while loops, and switch cases. And when we say that the pulse processing unit can run even the most complex quantum algorithms, what we really mean is that it can run the algorithms that live in this phase space that is spanned by these 4, right? Because each one of you can think of a flagship experiment, a new experiment that he or she desires to run. This experiment will always live in this phase space. It is some combination of generation, acquisition, real-time processing, and control flow. And we, of course, aim to cover this entire phase space. And the idea is that you should be able to run this very seamlessly. And I will show you some examples. And for that, we have the programming language called QA. Okay? So in QA, you can formulate any quantum sequence from Ramsey to error correction. I'll show you some examples. And then there is a translator, or if you wish, a compiler, that would compile your sequence in QA to the assembly language of the pulse processing unit, which will then run it in real time. So you may think to yourself, this is maybe a bit showy, this is just beautiful, but does it really work? Is it really valuable? So I have here by chance a quote by one of the organizers. Actually, Dr. Dohan was kind enough to provide this quote, not for this conference, it exists for a while. And he says the following: the OPX and QA platform completely changed the way we control semiconductor quantum dot spin qubits. Key qubit control schemes we previously developed individually using time-consuming hardware description languages are now implemented in one box. Okay, so completely changed. So I do believe that we bring a new paradigm that is essential for scaling up quantum processors. Now let's go a bit deeper. So from an architecture perspective, you may have your quantum system, 1 qubit, 50 qubits, doesn't substantially matter. The primary thing that we provide at Quantum Machines is these modules, okay? So the main module is the one that you see over here. This is called the OPX. This guy over here. And it primarily contains the pulse processing unit that I mentioned earlier and the analog front end. Okay. Now, together with the octave, which is the module just above it, it does the following thing. So it has the analog outputs up to 18 gigahertz, analog inputs up to 18 gigahertz, classical processing, and comprehensive multi-qubit control flow. And 18 gigahertz is very important because I know that many labs go to 10, 12 gigahertz. But of course, since this is still under research, maybe tomorrow you'll have an idea that requires 13 or even 15. So we decided to go all the way. The next very important layer is the stream processing. This is for example, in IBM language, this is the near-time processing. Okay, so you have the real-time processing and then the near-time processing. There's an additional layer of processing on the way to the user's computers for additional heavy lifting processing. The last layer is then just the network connectivity and the user's access, whether it is locally or through the cloud. Good. Now, this is an additional list of products that we have at Quantum Machines. I won't have the time to talk about all of them. These are the products that are offered by QDevil, our Danish branch. So, so let's start talking a bit about programming. So the idea I would like to convey to you is that it is extremely easy to implement any quantum sequence that you may have in mind. Okay, and you can, by the way, after the session, you can challenge me. So you see the program that you see over there is a real-time program. So this is a very simple and naive program. We call it a power Rabi. It will happen in real time. So this is a real-time for loop. Everything is going to happen in real time. Play pi times amplitude A to qubit 1. So I'm grabbing pi, which is a pulse that I defined in advance. I'm changing its amplitude in real time, and I'm sending it to my qubit 1. I'm also applying the FIR filter, IIR, the typical things that many of you know and use. Then I'm measuring the qubit. Measure the qubit always consists of sending a pulse to the qubit and getting a pulse back. I'm demodulating it, integrating. I'm doing everything needed in order to get the state estimation, the estimation of the state of the qubit. This is what you see here with I. Okay, so the parameter I is a real-time parameter, and it contains now the information about the quantum state. And the idea that I'd like to convey here is that you can, once you have this parameter in real time, you can actually go very wild. Okay, so I have here a nice example. So you see a sequence that goes as follows. So I have a condition that depends on a parameter that I just measured. So if I squared times cosine A is greater than 10, then play some optimal control pulse number 12 times I to qubit 12. Okay, and even though this seems like a very naive example with 2 lines of code, I would claim, to extent of my knowledge, there is no system that can just run this, okay? Analog feedback across a large-scale system, this is something that is very, very unique and very, very advanced and challenging. And the idea is, again, that you can go from the simplest things you have in mind, like a Ramsey that is here formulated with about 10 lines of code, all running in real time, including the averaging itself, and all the way to error correction. So let me show you an example. So this is a part of the CAT codes realization that was proposed by AWS in 2020. So this is the magic state distillation, which I guess many of you are familiar with, part of the error correction code. And as part of it, there is a piece of code which is called the stop algorithm. It is extremely challenging. Okay, why is it extremely challenging? Because it requires real-time complex control flow. So you see in real time, they require here to have cascaded while loops and if statements, okay, in real time. This is very challenging, and this is just pseudocode. But what I'd like to show you is that with our system, with Qua, you can actually implement it out of the box. Okay, so if you want to run, say, this AWS type of CAT codes sequence, you can actually run it tomorrow. Okay, if you have good enough qubits, you can actually run it. Okay, you don't need to develop it for months or years. It will actually work. This is another example just to show you that we're not all about superconducting qubits. I know the focus tomorrow will be beyond superconducting qubits, but this is a very, very advanced sequence with neutral atom arrays. So this is the rearrangement of neutral atoms in an array in real time with minimal jerk trajectories. This is cutting edge sequence. This was measured in Mark Safman's lab in University of Wisconsin, and very, very few places in the world can actually realize that. So The other aspect is to what extent are hardware and software scalable. Let's talk a bit about that, and I want to go back to the illustration that I had earlier. So it's easy to have, of course, to fill up a whole rack with modules. But the idea here is that it is scalable in the following sense. We decouple it into 3 elements. First, of course, synchronization. All modules work on the same clock. This almost goes without saying. The second is that there is real-time broadcasting between the systems. Okay, so if you measure something in one module, you need to be able to respond in the other. Okay, real-time broadcasting of information in real time, far faster than your qubits, between the modules. We're talking about an overhead of about 100 nanoseconds between modules. Okay, so active reset can happen within a module within 198 nanoseconds. This is extremely low. Between modules, you just add another 100. This is extremely low. The third aspect is from a software perspective, because if you have now a system that fills up half a rack or a whole rack, the question is how easy it will be to code. And what I will show you now is that from a coding perspective, it doesn't matter if you have a single module or 13 modules. From a programming perspective of your quantum sequence, it will be exactly the same. And I'm going to do it with a very well-known example. This is the bit flip code. This is the bit flip code in 3 minutes. Okay, so how does it work? How does the bit flip code work? Let me remind you. So the bit flip code goes as follows. So we have 3 data qubits that should encode the same information, right? These are the blue qubits, and we have 2 ancillas, okay, in order to track the errors and correct it. Now, by the book, it should work as follows. So first, I have this controlled knot. Then I measure, then based on that, I correct the data qubit, right? So this bit over here flipped because these 2 were different, right? This is how it should work by the book. But typically with transmons, it works slightly differently. It works as follows. So we have the same 3 data qubits. Now we do a pi over 2. We do a controlled phase. Then we do another pi over 2. And again, we can know where was the error, and we can correct it. So all in all, the sequence is quite simple: preparation, error tracking, and error correction. And what I would like to show you is that all of this can be implemented in about 200 lines of code, okay, with no development that is required on your side. 200 lines of code. So let's see this. So for example, I have here the preparation is over here. It's a bit higher than me. It's over here. Then we have at the bottom, we have the parity tracking, which goes on for a few more lines. Then I measure the ancillas. This is measure state. And then I have the correction. This is it. And this is not error detection. We're not just detecting it. We're correcting it. And it was very simple. However, you may tell yourself, what is this command, right? What is this measure state? Maybe it hides a lot of code because it looks like it's very brief, but maybe there's a ton hiding behind the scenes. But in fact, there is not much hiding behind the scenes. This is all you have, right? So we used a few macros, but this is all you have. This is the entire code for this bit flip. So if you have 5 good qubits in your lab, you can run this tomorrow, guaranteed. Now there's one more aspect why, or the main aspect why I'm showing this example is the following. So, and it is this thing. So you see, I have here a very naive for loop, which is looping over the qubits. And at each iteration of the loop, I'm actually actively resetting another qubit. And the idea in scalability here is that this thing will look the same for 5 or for 50 qubits. It doesn't really matter, right? For any number of qubits, it will look the same. However, it is also important to note that it is not just unfolding many lines of code with this for loop. This is easy. This has real-time implications, because you see there is an align command over there. Not sure if you can see over there. This means that in real time, whether you have 5 or 50 qubits or 100 qubits, they will all be synchronized, and the system will take care of it. Now, from a software perspective, you don't need to account for it, whether you have 5 or 50, whether you're using here 5 OPXs, 10 OPXs, 15, it doesn't matter. The system will take care of it. And with the lowest latencies, I believe that can be achieved. So this is from a scalability perspective. So we said from a synchronization, data broadcasting, and also from a software perspective. And by the way, here also I need to broadcast data from between all the modules, right? Because if I want to actively reset 50 qubits, I need to send the state estimations across all the modules, right? So this is a very advanced, very advanced sequence in just a few lines of code. So let's talk a bit about how fast do sequences and calibrations run. So I hope that many of you are experimentalists and can understand how important this aspect is. Because a lot of time can be, actually you can spend 99% of your time just calibrating, right? And 1% of your time measuring something which is of physical interest. So I'm actually using another quote that we have. It was not prepared for this talk. It was prepared, it was given to us a long time ago. So this is by Yoon-Jong Kim from Oscar Painter's lab at Caltech. So Yoon-Jong said, using this high fidelity, rapid readout and real-time state assignment, we were able to do an active reset and generate this noiseless plot in 20 seconds. Okay, so this is, he used our system for a 10 qubit device. He estimated it would have taken with an alternative solution way longer, and this resulted, so his work resulted in this paper, and we helped to some extent. And of course, Yoon-Jong presented this beautiful paper today, earlier today. And the thing is that we actually see these speedups all the time. So this is, for example, from David Schuster's lab at U Chicago. So this is a massive speedup. 5,000 times speedup is the difference between an hour and a month. Okay, and this is not just a calibration. This is a very complex sequence where you would do spectroscopy versus the displacement of the state of a 3D cavity. Okay, so this is pretty complex and requires massive real-time feedback. Another example, just a Ramsey. This is the good old Ramsey that was sped up by a very large amount. This is from Lincoln Labs in the United States. This is a Rabi chevron for those of you who are working with quantum dots. So this Rabi chevron used to take this lab an hour and a half. Now it takes them 4 minutes. And the beautiful thing here is that, in fact, in the background, it's not just about speeding up with active reset or real-time looping. In fact, in the background of this graph, we apply real-time feedback to compensate for the drift of the gates, right? Because some of the gates drift. And you don't want to compensate for that by going back to the PC, understanding how much it drifted, and then applying feedback. You actually want to apply this feedback in real time. This can save, as you see, a lot of time. And this is from a different angle. So this is from a collaboration that we have with Quantware. This is a company based in Delft that provides superconducting qubits. So here we're not looking at the speed up, but what we're looking at is kind of comparing two options, two schemes at equi-times. Both of them were run in 20 minutes, but since these were different schemes, you can actually see the impact of the quality. So of course, maybe I could get to this quality in this scheme as well, but it would have taken far, far longer, right? So this is just another way of looking at it. And the main message from this is that if you can speed things up, it also boils down to fidelity. Because if you can run your sequence, your calibrations far faster, you can actually get to much better fidelities. And we see that very often. Now, when going to a large number of qubits, there is another aspect, and that is not just a single sequence, but it is the orchestration of a great deal of sequences, right? Typically, this is done on a graph, a calibration graph, where you have many, many parameters, and you need to calibrate them all. So here I have just one. OK, so this is already on a few qubits. And we have here a graph that shows the runtime improvement on a very long sequence of sequences, right? So the typical thing that you want to do if you have many qubits is you need for every qubit to run many, many sequences. So for example, here we have resonator spectroscopy versus power qubit spectroscopy, rough and fine, power Rabi Ramsey to find the frequency, find the state discrimination, set up the active reset, readout frequency optimization, repeated pi, all x, y, randomized benchmarking, and drag optimization. And the more qubits you have, the more this will consume your time. So this is an extremely important consideration when designing a control system. So I hope that I helped shed light on this question of what really matters when designing a control system that can take you from 1 to 100 qubits and from Ramsey to quantum error correction. And the way we view it is that first, you need an architecture that can support cutting-edge sequences, again, without development time, right? If you can do it in 1 year, it doesn't count. The second is you need heavy processing in real time for ultra-rapid runtimes and calibrations. And the third is that you need scalable hardware, but equally software and programming. These are all crucial aspects. Thank you.
Thank you, Itamar. So we have time for a couple of questions. Is there any question for this talk?
Hi, this is I'm Kevin from KAIST. I'm going to the speaker of the next talk. I'm just wondering how you're going to how this can be included in the actual application programs. I mean software. I mean this is kind of you're providing very nice libraries and modules, I think, but it should be also used in larger pieces of software. Could you?
That's right.
Explain that?
That's right. Yeah. So what our customers typically do is so it depends whether this is in the context of an academic lab or a company. Right? In the context of an academic lab, so this is pretty easy, right? It's just this Qua, the language that I showed you, is simply what you use, right? And sometimes you just need to include next to it some controls of other instruments that you have in the lab, right? So that they can work all together. When we're talking about quantum computing companies, then this is a bit different because it is integrated into a set of compilers, right? Because then what you have is, what companies do is they have a compiler, a translator from higher level languages, let's say Qiskit or Cirq or others, that are then compiled down to Qua, to our language. Typically they would go through some other standard like OpenQASM 3 and then compile down to the language Qua. Thank you.
Thank you. Any more questions? So you have introduced some users, and they presented good user feedback. So if you can tell, so how large system have you delivered to a customer? So you are talking about 100 qubit-ish, but how big system did you really implement it instead of just having visions or plans?
So I'll tell two things. So first of all, we work with different types of qubits. So for example, if you talk about neutral atoms, then even hundreds, right? Because it's much more easily scalable. For superconducting qubits, so we're talking about the tens, the two-digit